In this lecture, we will study the practical models of operational amplifiers. Ideal op-amp model is very simple. We assume that the currents entering the input terminals of the operational amplifier is zero. And we are also assuming during the ideal operation V2 is equal to V1. In other words, the voltage difference between the input terminals is equal to zero as well. However, on the other hand, when we look to the internal schematics of an op-amp, we realize that this circuit consists of very many nonlinear elements and has many imperfections. And for some cases, we need to take into account these imperfections and nonlinearities and create a more precise model of the operational amplifier. At this point, I would like to mention a very nice quote from Albert Einstein. He states, "Make everything as simple as possible, but not simpler, because the complexity is the enemy of efficiency." So, linear circuit analysis is easy. As we have studied before, we have methods such as node voltage analysis, mesh current analysis, and superposition, which allow us to analyze circuits systematically. If we follow the rules, we end up with the correct analysis of the circuits. So, since we have these strong tools for linear circuits, we need to modify the ideal op-amp model by adding additional linear circuit elements to take the imperfections into account. This is what we will do in the remaining part of this presentation. So here we see three operational amplifiers in the inverting configuration. And since we know what the gain is, we can state that the gain should be equal to 5 for all of these three circuits. However, when we look closely to the resistor values, here we see 10 ohms and 50 ohms. Here we see 10 kilo ohms and 50 kilo ohms. And in the third one, we see 10 mega ohms and 50 mega ohms. Theoretically, according to the ideal operational amplifier model, all of these three circuits should behave the same. However, we should only use the one in the middle with reasonable resistor values, and in the remainder of this lecture, we will understand why we need to use 10 kilo ohms and 50 kilo ohms instead of the very low resistance values and very high resistance values. Here we see different parameters of certain operational amplifiers. We can find these parameters in the datasheets, and we will be learning how to incorporate these type of parameters into the models of the operational amplifiers. For instance, these are the bias currents, offset currents, and also other parameters such as common mode rejection ratio and gain bandwidth. Let us have a look to the offsets model of the operational amplifier. Normally, we assume I1 and I2 flowing into the input terminals of the operational amplifier is zero. However, this model assumes that there is non-zero bias currents IB1 and IB2 and also a non-zero input offset voltage VOS. In other words, the difference between V1 and V2 is not equal to 0, but it is equal to VOS. What are the effects of the bias current and offset voltage to the op-amp output? So we are engineers, so let us analyze this circuit using a practical example and see what the effects will be. We will need to consider the effects of the offset voltage and bias currents for operational amplifiers for each topology and circuit we are designing. So for some applications, these voltages and currents might be acceptable. For some applications, they might not. How can we analyze these type of circuits? We can analyze them using the superposition principle. Now we are solving this circuit using superposition principle. we need to consider all the current and voltage sources one by one. Let's start with V in. I will need to short circuit VOS. I will need to open circuit the IB1 and IB2, and I end up with this circuit. And this circuit is in the regular inverting amplifier topology, and V out is minus 50 kilo ohms divided by 10 kilo ohms times V input, and accordingly V out is minus 5 times V in. Now we will need to find the output of the circuit for the input VOS and for the input IB1 and IB2. In the first step, we solve the circuit for the input V in. Now I will solve the circuit for the input VOS by short circuiting the V in and open circuiting the IB1 and IB2. The resultant circuit is here, and now we will need to analyze the circuit. Here I have the ground, and here therefore I will have VOS, and accordingly here I will have VOS as well. No current will flow this way to the negative inverting input terminal of the operational amplifier, and now I will need to analyze the remaining part of this circuit. Here I have V out. So I would like to point out that even though we are working with a more complicated model of the operational amplifier, when I am solving all of these sub-circuits, I am solving it according to the rules of the ideal operational amplifiers. So how can I find V out? V out can be found using the voltage divider rule, and it will be 50 kilo ohms plus 10 kilo ohms divided by 10 kilo ohms times VOS. Accordingly, V out is equal to 60 divided by 10, 6 VOS. So now I found the output of the circuit due to the offset voltage. Now let us consider the input IB1, the bias current for the inverting terminal of the operational amplifier. If I disregard all the other inputs, my resulting circuit is shown here. How will I analyze the circuit? The reference node here will be at 0 volts, and therefore we have 0 volts here as well. And if I have here 0 volts, I will have in the negative terminal 0 volts as well. And here I have 0 volts too. Now, here I have 0 volts, and here I have 0 volts, and in between I have this 10 kilo ohm resistor. From the potential of 0 to the potential of 0, if there is in between a resistor, no current will flow. Therefore, this current will be equal to 0. However, I have here this current source, and the current IB1 will be flowing downward. It can obviously come over this 50 kilo ohm resistor from the output of the circuit. If this is the case, I have a resistor which is 50 kilo ohms over which IB1 is flowing. V out will be simply 50 kilo ohms times IB1, and this is the third output of the circuit. Let's look to the case where I have only IB2. When I short circuit the voltage sources and open circuit the IB2, I end up with this circuit. Here I have 0 volts at the ground. Here I will have 0 volts as well. And that 0 volt will be reflected to the inverting terminal too. And since this IB2 will not be affecting anything, and I have here 0 volts, my V out will be 0 volts too. Now we are seeing that IB2 is not affecting anything, but this does not mean that in another circuit with a different topology, it would not have had any effects. So it just shows only for the specific Opamp topology and circuit I have, this time IB2 is not having an effect. You will need to analyze your circuit for different operational amplifier topologies every time, and in those cases, IB2 might have an effect. What is the last step in the superposition principle? I need to add all the outputs of sub-circuits. Accordingly, Vout will be equal to minus 5 times Vin. This is the output of the ideal amplifier. Plus 6 times VOS due to the voltage offset. And plus 50 kilo ohms times IB1. And for the fourth one, I have 0, so I will not write that. So this is the output of the circuit, and these are the additional terms due to the offset model of the operational amplifier. Now we have found the output voltage of this circuit, taking into account the offset voltage and input bias currents. And specifically the offset voltage is 6 times VOS plus 50 kilo ohms times IB1. For a type 741 op-amp, we have the VOS is as 5 millivolts and IB1 as 500 nanoamperes. Accordingly, the offset voltage for 741 op-amp for this specific topology will be 30 millivolts, which is 6 times 5 millivolts, plus 50 kilo ohms times 500 nanoamperes, 25 millivolts. At the end, total 55 millivolts. Depending on one application, 55 millivolts might be acceptable. In some applications, it might not be acceptable. For instance, if we have a sensor, which is the input voltage, and that sensor has an output of 1-2 millivolts, 55 millivolts will be very high. But if we just are making a crude application and the output will be around 10 volts, and this will be changed by the bias by 55 millivolts, we might not care about it. But if this is not acceptable, you either change the topology of the circuit, and if that is not possible, you just go and buy an op-amp with better characteristics. This will cost higher, but there are thousands, if not millions of different types of operational amplifiers with different characteristics, and you will be able to definitely find one which suits your technical specifications. The op-amp in the finite gain model consists of two resistors, R1 and R0, and a voltage-dependent voltage source with a gain A. Let's analyze the circuit. The Vout is equal to A times V2 minus V1 plus R0 times I0. From here, I can extract V2 minus V1 as V0 minus R0 times I0 divided by A. If I take this and take the limit of the expression V2 minus V1 when A goes to infinity, then the result will be equal to 0 because A is in the bottom part, and when A goes infinity, this expression will be getting smaller and smaller. So now let us see what is I1. I1 is entering to the inverting terminal of the operational amplifier. What is I2? The current which is entering to the non-inverting terminal of the operational amplifier. I1 is equal to minus V2 minus V1 divided by Ri. And I2 is equal to V2 minus V1 divided by Ri. So when A goes to infinity, V2 minus V1 goes to 0, and accordingly I1 will be going to 0 as well. And similarly, I2 will be equal to 0 as well. So remember, in the ideal operational amplifier circuit, we were always stating that the currents entering to the input terminals of the operational amplifier is equal to 0. Yes, here we see why that was the case. In short, when we are setting the gain A to infinity, the finite gain model converges to the ideal operational amplifier models. But what happens when this is not the case? Because in real circuits, the gain of the operational amplifier is very high, but it is not infinite. It is in the range of 100,000 to 100 million. Again, since we are engineers, we need to have a circuit and quantify the effects of the finite gain model based on that example. And whenever we will have a new topology, we will do the same analysis again. Here in this question, we have a unity gain follower. It is a buffer circuit. It takes an input and it just brings it to the output. The gain of this circuit is equal to 1. And here on the right, I replace my op-amp with the finite gain model of the operational amplifier, and this is the resultant circuit. Here we are given the values of R1 is equal to 1 kilo ohms, RL is equal to 10 kilo ohms, and the parameters of the practical op-amp for the finite gain model are given as Ri is equal to 100 kilo ohms, Rout, Ro is equal to 100 ohms, and the gain A is equal to 10 to the 5. So what will be the gain of this circuit if we take into account the finite gain model of the circuit and calculate it according to the values provided here? So we need to do the circuit analysis for this case. Alright, how will I analyze this circuit? So let's have a look. I have here V0 and I observe that this is connected directly to this node. And I can say that this node is V0 as well. Wherever I see V1, I replace it with a V0. Now, what else can I do? I can write the Kirchhoff's current law for this node and also for this V0. So let's write it first for V2. V2 minus Vs divided by R1. This is the current going this way. And now I need to add the current going this way. Plus V2 minus V0 divided by Ri is equal to 0. From here I can find V2 as Ri times Vs plus R1 times V0 divided by Ri plus R1. And I can actually write this with the separated terms, Ri divided by Ri plus R1 times Vs plus R1 divided by Ri plus R1 times Vout. So this might be an important equation. This is the KCL. From KCL we found V2 as a function of Vs and V0. Now what else can I do? I can try to write the Kirchhoff's current law for this V0. We have the current going out this way, which will be V0 over RL, plus current going this way, which will be V0 minus A times V2 minus now V0 divided by R0 plus the current going this way, V0 minus V2 divided by Ri, and this will be equal to 0 as well. And this is my second equation. I can try to write this in a way I will collect all the V0 terms on the left side and all the V2 terms on the right side of the equation. Let us try to write this V0 1 over L plus A plus 1 divided by R0 plus 1 over Ri will be equal to, on the right side I have minus A times V2, so it will be a plus A over R0 plus, from here minus will become plus 1 over Ri times V2. Okay, this is a beautiful expression because now I can go and take this expression for V2 and plug in here. Let's see what will happen when we do that. This is becoming messy, but I sense that I am making progress towards solution. It's all about good accounting in solving these type of questions and in general in engineering. So I will multiply this by Ri over Ri plus R1 times Vs. And another term which is related to V out, which I will need to take to the left side. Alright, let me define this term as alpha, otherwise it will be very messy, and try to take this term to the left side. V0 times 1 over RL plus A plus 1 divided by R0 plus 1 over Ri minus alpha times R1 divided by Ri plus R1 will be equal to alpha times Ri divided by Ri plus R1 times Vs. Now, can I find gain? Gain will be equal to V out divided by Vs. This will be equal to, let's just kind of like try to write this. Alpha times Ri divided by Ri plus R1, and this whole term 1 over RL plus A plus 1 divided by R0 plus 1 over Ri minus alpha times R1 divided by Ri plus R1. And I found my gain. Now I have all of these values of Ri's, R1's, RL's, and so on and so forth. I will go to MATLAB and calculate the gain value for the specific example we have, and this will be equal to 0.99989. So this is a value very close to 1, and all of these finite gain model parameters with the gain A and Ri and R0 affected our circuit minimally, and our gain shifted from 1 to 0.99989. So in this case, the finite gain model was not necessary to use for the unity gain operational amplifier circuit. In reality, the finite gain model of the operational amplifier can be more accurately expressed as the summation of A times V2 minus V1 plus A common mode times V1 plus V2 divided by 2. So V2 minus V1 is the differential input voltage at the input terminals of the operational amplifier. We have this gain A, which is a very high value on the order of around 1 million or so. And then now we have this unwanted common mode gain, which multiplies V1 plus V2 over 2, basically the average of the input voltages with some type of coefficient. So we are defining the common mode rejection ratio as the ratio of A to A common mode, and we want this CMMR to be as large as possible. We should consider CMMR only when measuring very small voltage differences at the presence of high common voltages. So basically, if we are operating close to the rail voltages around 13 volts or so, then CMMR might be an important parameter to consider. In electronics, everything depends on the frequency. And in the finite gain model of practical op-amp, the gain A does not depend on the frequency, but in reality it does. And here is the relation. The gain A is equal to B divided by omega, which is the frequency. So when the frequency increases, the gain of the op-amp decreases. So therefore, we want an op-amp with the greatest possible gain bandwidth product such that we can use it in order to track high frequency sinusoidals.